Hello everyone, my name is Khanh-Binh Nguyen from Nguyen University, and today I'm gonna present my work named Debiasing, Calibrating, and Improving Semi-supervised Learning Performance via simple ensemble projectors. So we're gonna go through the background of the semi-supervised learning. Semi-supervised learning contains of two phases. The first phase is training the model on the weak augmented label data. So then we can let the model learn the correct prediction from the ground truth. Then using the trend model, we continuously feed the weakly and strongly augmented unlabeled data through the model to get the prediction. With the weakly prediction, we take the highest prediction at the pseudo label and use them to train the strong prediction with the supervised manner, and this iteration repeat numerous times until the model is converged. However, the problem is due to the high threshold of the semi-supervised learning, the semi-supervised learning model is easily overfitted to the small label training datasets and produce the overconfidence in correct prediction as we show in the figures, and they produce the high diversion between the strong and weak prediction as well. To mitigate them, CoreMath and SimMath propose to use a projector to map the filter map into the smaller embedding space, and using the embedding space to aggregate into the prediction and have to improve the prediction. However, using the embedding in the choice contrastive training scheme at CoreMath or SimMath still suffers from the confirmation bias. And when the confirmation bias happens, the wrong prediction from the classifier can affect into the label embedding space, and this repeated numerous times can harmfully hurt the model and then degrade the performance of the model. So to solve the problem, we propose EPASS or Ensemble Projector Aided for semi-supervised learning with a very simple technique that we create k number of the projector instead of using only one, and then after we project the value through k projector, we take the mean of them, so then we can have the mean label embedding. So the core idea is, since we create k number of the projectors, and at the beginning each projector can have different initialized values, so then it produce different aspects at the beginning of the training, and then by using the mean of them, we can mitigate the effect from the confirmation bias on the very beginning of the training, and by having the better embedding space, we can improve the performance from the classifier layer and vice versa. So we evaluate our method EPASS by combining it with CoreMath and SimMath on small datasets such as Cipher10, Cipher100, SVHN, and STL10. And as we can see that when we use the EPASS with CoreMath and SimMath, it consistently improve the performance by a large margin over all of those datasets, especially for the CoreMath on the imbalanced datasets such as SVHN or STL10. The improvement is quite visible. And we also evaluate them on the ImageNet dataset under three different training scheme, 100K of label data, 1% and 10% of label data. And EPASS also showing that it consistently improve the performance of conventional COMAS and CMAS quite a lot. And here, with the large scale datasets, the CMAS show the better performance than COMAS when using with the EPASS. We also benchmark our performance on the imbalanced datasets such as Cipher 10 long tail and Cipher 100 long tails, and using CMAS also improve the performance of conventional COMAS and CMAS. In these figures, we showing the pseudo-label quantity versus the quality on the ImageNet on the left figure. As we can see that using EPASS, we can improve the quantity as well as the quality by a large margin on both methods. And on the right figure, we're showing the accuracies by epochs of the conventional method and the conventional method using EPASS. And EPASS can have the model accuracy increase much faster than without the EPASS. To better understanding about the calibrating effect from EPASS, we measure the expected calibration errors (ECs) on ImageNet 1% as showing below. We can see that by using EPASS, we reduce the ECs on COMAS from 2.41 to 2, and especially on CMAS, this value is larger from 6.85 to 1.94, as well as we evaluate them on the ImageNet 10% as well, and this also visible on the over both methods. Thank you for listening.